This helicopter heat exchanger is half the size and 4 times more efficient than the one it's designed to replace.
An audience-selected winner of our Cool Parts Showcase on this episode of the Cool Parts Show. The Cool Parts Show is brought to you by Carpenter Additive. When it comes to managing metal powder, there is no one-size-fits-all approach. Stick around after the episode to learn more. I'm Pete.
I'm Stephanie.
Welcome to the Cool Parts Show.
This is our show all about cool, unique, interesting, amazing, and now award-winning 3D printed parts. So in 2021, we ran our first ever contest, the Cool Parts Showcase. We got dozens of entries. Pete and I got to choose the finalists, but you, the viewers, got to vote and choose the winners. And we have one of those parts here in the studio with us today.
The Cool Parts Showcase. This was so much fun. We had finalist parts on display at the Additive Manufacturing Conference and Expo. We had winners in each of 3 different categories based on 2,500 votes we got from the audience. So this part right here is the winner in the category Best Proof of Concept.
Yes, so this part is a heat exchanger for a helicopter. It was designed and submitted to us by Advanced Engineering Solutions.
Right, a heat exchanger for a helicopter. This is a proposed replacement for a heat exchanger on a military helicopter, been in service for decades. This particular heat exchanger cools gearbox oil, and it uses the helicopter's own fuel as the cooling fluid. The conventional heat exchanger uses shell and tube design, which is typical of heat exchangers, meaning so tubing is bent around in an array parallel to itself, and the cooling fluid washes over that. What is special about this metal 3D printed version is on the inside. The complex geometry on the inside provides for much more effective heat transfer than that conventional design.
Right, and there's a couple of other things going on here too. So that conventional tube and shell construction that you described, very labor intensive, lots of different parts coming together, and it might mean that you're carrying more material, you're carrying more weight than you might want to. And as we know with aerospace, like lightweighting is almost always part of the goal. And so the ability to 3D print something like this in just one piece dramatically reduces the assembly, simplifies the manufacturing, and also can help remove weight and material out of the heat exchanger.
Labor savings, weight savings, there was space savings too. So this heat exchanger design is 1/2 the volume of the existing heat exchanger, and it's 4 times more effective at cooling.
But key to a lot of the things that we're talking about is what's going on in the inside, some features that are not easily seen from, at least from this angle of the gearbox. But on the inside, instead of all of those tubes bent together, this thing is actually packed full of gyroids.
Gyroids. So these mathematically complex surfaces that in the case of this heat exchanger provide for an optimal relationship between the metal surface area and the 2 fluids, enabling more effective heat transfer. To talk more about this, let's bring in the designer of this heat exchanger. This is Dr. Andreas Vlachinos, and he is Chief Technical Officer with Advanced Engineering Solutions.
Nature is using these geometries for a long time. Soap bubbles are very good examples. If you have 2 rings and you dip them in soap water and bring them out, it generates a nice, beautiful surface, which is not cylindrical. It finds the minimum possible surface area which connects those 2 rings. We call that minimal surfaces because they minimize the surface, but because the soap bubbles, it stretches itself and automatically nature finds the optimum designs. These designs, if they're periodic, we call them triply periodic minimal surfaces because they repeat themselves in all 3 directions. So triply periodic minimal surfaces, and some of them are gyroids or diamonds. These surfaces exist in nature. Butterflies use them in the wings so they can have a high span to thickness ratio. And a lot of other biomimicry type applications can come up out of that. The problem was These surfaces were not discovered in the late 70s, and then when they discovered, we just had the equations. I was so excited about them, but you couldn't do anything. We couldn't manufacture them, and we couldn't build them in the CAD systems. Now, with additive manufacturing, we can build these surfaces because they don't need machining.
So Andreas just spoke about how 3D printing enables us to build these interesting geometries like gyroids that would not have been possible previously. But in this case, the gyroids actually help with the 3D printing because they are self-supporting.
How's it 3D printed?
This was made with laser powder bed fusion. Specifically, EOS printed this on one of their M290 machines. It went through just minimal post-processing, really just threading these holes and a little bit of surface finishing, and it was printed without supports, so almost exactly how you see it here.
So laser powder bed fusion, what's the material?
This is aluminum silicon 10 magnesium, so it's an aluminum alloy.
And there's no support structures?
So not in the way that we typically think of them. So the gyroids themselves are self-supporting, but you can't just build gyroids like free-floating in the powder bed. So if you take a look through the bottom of this heat exchanger, you'll see a lattice on the inside. And that lattice is really just there to provide a surface that you can build the gyroids on top of. But it's not a support structure that would be removed afterwards. It's something that has become a feature of this part. It's built in, it's not coming out. So it's a support structure, but not in the way we maybe usually talk about them.
Okay, there's that lattice on the inside. There's a lattice on the outside. Like, it looks like a Fabergé egg. Like, what's that?
Yeah, so also kind of a support structure. So these kind of crisscrossing ribs are here to allow for the wall thickness to be thinner. So because you have this support on the outside, you can build a thinner wall without losing the strength. And this allows, again, for material savings and reduced weight.
The mission in especially aerospace things when they fly is to minimize weight. Of course, you don't want to compromise safety. So instead of making it very thick, we put ribs outside, which they enhance the performance. And the ribs, wherever there is, a dip, they're thicker. They're not uniform in height, number one, so for the outside. So there is a lattice structure, 2.5D lattice structure wrapped around outside. Inside, also, there are lattice structures which they act as a screens. You try to double dip. Those screens act also as supports for the gyroids. These gyroids have three amazing properties. First of all, if we infill a volume with a gyroid, it splits the volume in two different domains, two different volumes. They don't touch each other, and they're continuous, which is ideal for heat exchangers. You can pump fluid in one and pump the other fluid in the other, and they intermingle very well. The second amazing property, they don't have a weak axis. They can't bend like that. They continuously turn, so they're very, very strong in compression, for example. So this thing, it goes about 10 times the required performance for pressure. And the third feature, they keep turning themselves up, so they don't need supports. So when you print them, you don't need to have any supports inside, because how would you be able to send somebody inside here to remove the supports? That would be very difficult. So the entire thing was printed with no supports. And of course, not bill failures because we did simulation.
Andreas talked about simulation, and that's a really important part of this project. A lot of the engineering was done digitally in the form of simulation. So the fluid flow and the heat transfer were simulated to get the design right, and then the additive manufacturing build was simulated first before it was ever produced physically.
Right, so the software was a huge piece of this, not just in figuring out the design, but in proving that the design was going to work, proving that it was going to print correctly before they actually went to the printer. So Pete, refresh my memory, like what were some of the software tools that they used?
Fluid flow was simulated. Computational fluid dynamics was used to look for things like recirculation regions, places where the fluid got stuck in a loop, meaning it wasn't performing in a power efficient way. So the software used for that simulation came from PTC and from ANSYS. And then the laser powder bed fusion build was simulated also before it was 3D printed, and the software used there was from Additive Works.
So the physical object that we have here is actually the result of a whole lot of virtual digital work before they ever got to the point of 3D printing. So this heat exchanger, it works as it was designed. It's more efficient than the conventional alternative, and it was printed without build failure.
Right, and I want to draw a circle around that, just how important and how powerful the simulation tools prove to be. We talk a lot about how additive manufacturing is an aid to invention. It's easy to iterate with additive manufacturing, keep making part after part after part after part until you get exactly the design you want. But digital simulation can be an even faster way to develop a design, iterate virtually, and that proved to be very important here. The fluid flow properties were nailed down in advance, and the recirculation regions that I mentioned, some of those were found, and it led to modifications in the design before it was ever made physically. The additive manufacturing as well. We've talked about also how in additive, metal additive in particular, there's trial and error involved. That's part of process development, except software tools are bringing more and more sophistication to the table here as well. In the case of this particular part, there wasn't trial and error in terms of physical build. The build was simulated first, and it allowed the first part printed to be a good part.
So this is digital simulation and digital manufacturing in the form of 3D printing working together.
So you can change something and you see immediately the impact of your change on the design performance. So you can do really cool stuff. It's like having a spell checker for the design real time. If you do that freedom, you're not afraid to try crazy ideas.
All right, are we ready to wrap this up?
I think so. You start.
All right, so this is a heat exchanger for a helicopter. This exchanger cools the oil, the gearbox oil for the helicopter with the fuel of the aircraft. So conventionally a heat exchanger like this would be made with like a tube and shell construction where you've got a lot of different tubes running through it that have to be bent and assembled together. Here, this was 3D printed in just one piece. So this exchanger was designed by Advanced Engineering Solutions. And in this case, the tubes are replaced by internal gyroids and lattices, which allow for this heat exchanger to be smaller, to be more compact, to be lighter weight, and also to function more efficiently at cooling that oil.
Yeah, more efficient design, and that efficiency comes from an internal geometry that could only be produced through 3D printing. Simulation tools were used to arrive at that geometry and to simulate the build in advance. This was made from an aluminum alloy on a laser powder bed fusion machine from EOS M290. Minimal post-processing, some machining at either end for the connection to the rest of the assembly, but otherwise, this is one solid 3D printed piece replacing what used to be an assembly and ready for long service life on a military helicopter.
All right, I think that'll do it. Thank you again to Advanced Engineering Solutions for submitting this part. Congratulations on your win. We're going to be doing episodes with the other winners as well, so keep an eye out for those.
Yeah, more episodes coming up with Cool Parts Showcase winners. Subscribe so you don't miss those. Catch our back episodes. If you're seeing the show for the first time, they're all at thecoolpartsshow.com.
One important note, you do not need to win a contest to be featured on The Cool Part Show. So if you do have a cool part you'd like us to consider for a future episode, you can email us coolparts@additivemanufacturing.media. Thanks for watching.
This episode's brought to you by Carpenter Additive. We're past the point of not knowing how to qualify metal 3D printed parts. We know, it's just that different end users of those parts have different qualification requirements. Additive manufacturing service providers have to navigate that, and Carpenter Additive has to think about that in tailoring powder management solutions.
Our customers typically will have, if they are a service provider, they will have a series of end user customers who may be, say, OEMs in the aerospace world. And each of them has a fairly large team of engineers who've been doing this for decades or more and have developed all these standards, regulations, paperwork. So it is certainly a challenge to thread the needle between all of these different requirements. We start really high level, we walk on the shop floor, We ask them about, okay, source to sink, how do you bring in the materials, goods in, send that material to each of the systems, and then what we're really interested in is how do they reuse that material. So what we do is called a value stream map. Pretty often that leads to a series of things that were either overlooked or hadn't really boiled up to the surface yet in terms of things that are potential risks or potential challenges or inefficiencies that exist. A lot of the customers we work with, especially in the more regulated industries such as space or medical or aerospace, have already been through those early learning stages. They've put 5+ years into this. They've done the product design and the design for additive manufacturing. And now they're starting to reach some of the more finicky problems that you get when you're at the scale of maybe 5-10 machines. You're running different materials simultaneously, you're doing different programs. We get to take the best from the medical field and the aerospace field. We understand the specifications and the standards that exist in each of those fields, and we can sort of take the best elements of those and customize that to our customers.